Okay, good afternoon, everybody. Okay, so in this session, I will be looking at experimental investigations of turbulent canonical flames, and I'll be delivering this in partnership with Professor Gaetano Magnotti. Okay, so some of the aims and the general vision of this session. What do we mean by canonical flames? So one of the ideas here is that we're intentionally trying to avoid multiple complex phenomena occurring simultaneously in one flame. And so this is intentionally going in the direction of opposite to a complete industrial burner, but we're trying to take particular phenomena and understand that in one configuration. And perhaps we could lean on and draw inspiration from a lot of the success that's been occurring over perhaps the past 20 to 30 years at the TNF workshop and that similar community. So the next key component of this is, well, when we have this experiment to explore this particular phenomena, we want to apply very detailed, high fidelity measurements to it. And historically, these benchmark data sets have been relying on multiscalar measurements that have been relying around, say, Raman-Rayleigh diagnostics. Now, there might be some particular cases in a premixed combustion case in certain scenarios where, say, simple Rayleigh scattering to derive temperature may be sufficient. But generally speaking, we would like to have mixture fraction and temperature simultaneous and other minor species. So certainly not particularly simple measurements, but very challenging measurements that only a few laboratories around the world historically have been able to deliver. So what I'd like to do is to, well, before we jump into this, I'll say straight away that right now, as it stands, we don't have any fantastic canonical flames with the sort of measurements that we would like to deliver to the modeling community for validation, sitting here right now to deliver and take to the modelers and say, we've got a nice suite of data and it's published and it's ready to go. The idea is that this is really a work in progress, and what I'd like to do, at least in some of this talk, is to show some of the potential candidates that are going in this direction, as well as some sample results that we've got. And I think Gaetano, when he's presenting, he'll present some of the more mature measurements, and I'm here to try and present some of the encouraging measurements that are, well, encouraging experiments and encouraging measurements that are being done. So the first group that we've got some momentum moving along is from Darmstadt and NTNU, and they've got three canonical configurations that they're actively working on. One is this a post-flow jet configuration. Now that certainly can be in a laminar configuration, and the idea here is that we've got a nice way to explore laminar flames using and validating our detailed diagnostics. And I think the key point here is that we can put the laser beam through the middle of the burner and we can resolve this reaction zone in a normal fashion. The next one is their multi-regime burner. Now their multi-regime burner historically has had a number of publications and great momentum on it using methane or carbon-based fuels. So the idea of applying this to ammonia-based fuels, it's worked fantastic as a model benchmark. Again, the idea is going forward using something similar for ammonia certainly would have great value. And also they're developing and they're looking at piloted turbulent jet flames in, I guess, what you might term a McKenna burner with a central jet tube. So generally, the idea of some of the work that's been moving forward, they're able to show that in their opposed flow burner, trying to set up certain configurations where we're looking at moving towards extinction. I think as we saw in some of the previous slides looking at reaction, that this has been, a lot of work's been focused on laminar flame speed, which is very tough, but certainly in turbulent configurations, we're interested in when do you start to get extinction? And so extinction strain rate, even if it's in the laminar flame regime, is certainly very relevant. And it's a great opportunity in these laminar flames to at least validate the Raman measurements or detailed measurements, and it's in a known configuration, and we can at least attempt to compare major species, which we should be predicting quite well from our simulations to the measurements, bearing in mind that these sorts of measurements are somewhat new and there's all sorts of challenges that are needing this validation. And then, of course, some of the other ideas is that in their jet flames is to understand the radical structure that's occurring. So an important point here is that the momentum in this direction at the Darmstadt group, they've got a history behind them and developing diagnostic techniques, using this multi-scalar configuration, and they've been doing some work developing and adapting their configuration to ammonia-based flames based on Raman-Rayleigh diagnostics. Okay, so another group that I think has perhaps got some good publications that are just recent, that are going towards what we could call model validation, is from Lund, and they're looking at high Karlovitz premix, high turbulence intensity, so high Karlovitz number premix flames, and they've produced a similar burner to what I'm just presenting from Darmstadt, a similar sort of McKenna burner with a central jet tube. And they've a distributed reaction zone burner that I think you could liken to be very similar to the Michigan high piloted burner. So they've got two recent publications in Combustion and Flame and one in press from the Proceedings of the Combustion Institute. And I think what's relevant from the paper from the Proceedings of the Combustion Institute is one of the first, one of the the early publications where there's both the simulations and some degree of experiments to compare the two. Now, I will completely acknowledge here that the comparisons here are based on planar NH-PLIF measurements. So it's not multi-scalar, but it's at least going in the right direction. They're trying to join experiments that are model validation capable with some kind of diagnostics to validate the simulations. I'd also note that with their experiments, they have some velocity measurements, which is going in the right direction for model validation and understanding boundary conditions. And they've also got some other measurements of temperature in these. And so I guess this is just taking some figures from their paper to show experiments and simulations. And this is just, at least in these figures here, a qualitative comparison. Okay, stepping gears to another group, they're the group from Sydney. So this is work that we're working on, Professor Asad Masri and Dr. Andrew McFarlane and myself. This is utilising the hot co-flow burner, which is a configuration which is well studied and has featured many times under different configurations, particularly in the hydrogen or using methane in the TNF conference, and many simulations have explored this burner. And so the idea here is that can we try to explore and use this configuration for ammonia or ammonia hydrogen mixtures, with the real idea here is that we've potentially got some mixture of stabilization modes between flame speed and auto ignition. So some of the ideas here is that if we were to say, let's just leave the hot co-flow temperature constant, and we vary the amount of hydrogen mixed with our ammonia, how does that impact the liftoff height? And the point that I'd at least like to make here is that between 12.5% and 15%, that's a small increase in the percentage of hydrogen, and likewise going from 15 to 20, we have some sensitivity that we'd like to see when we're in experiments. We're interested in experiments that display sensitivity to the liftoff height. So there's some range for a given co-flow temperature that we can explore some sensitivity. And so the idea here is that, is this a useful configuration, and what's the conditions that we should be hunting down for further study? Perhaps something else that we'd highlight from some of these experiments, again, if we're looking at percentage hydrogen in our ammonia mixture, in that for some configurations, there's very, very small amounts of chemiluminescence. You could argue potentially not really a real reaction zone in the turbulent flame when we've got zero hydrogen, so pure ammonia. And then for a very small amount of hydrogen, only 2.5%, we've got a brightly luminous flame. And so the idea here at least is that there's a great sensitivity to a very small percentage of hydrogen under this particular configuration. That's with a co-flow temperature of about 1450 Kelvin. So I think at least if we go back to the Cabra configuration for the hot co-flow for hydrogen, we remember that part of the interest in this flame was the great sensitivity to co-flow temperature, that we could get a lifted flame right the way through to a seated flame for a very small range of co-flow temperatures. And so that's what we're trying to extract from this data here is to understand, well, where are we sensitive to co-flow temperature? And in this case, we're looking at percentage of hydrogen. And or we could say, let's keep the hydrogen concentration in the jet constant, or percentage of hydrogen mixed in with our ammonia constant, and vary the co-flow temperature. And what's the sensitivity? Generally speaking here, at least for these hydrogen concentrations that we're presenting here, that we've got a much wider band of liftoff heights. It's not similar to, I don't want to say exactly similar, but it's a wide band similar to methane. It's certainly not a narrow 50 Kelvin band like we saw in hydrogen. And perhaps this is certainly not the focus of this talk, but in an ASPAC talk later on I believe Thursday, where we're looking at where we've got one of these flames and we've got a premixed, and in some cases, auto ignition kernels are relevant. Okay, so the summary there is that we've got some platforms and that are the well-established boundary conditions that are amenable and that are encouraging, and that some of these experiments in the different universities are developed their parameter space, and certainly these is that we've got some encouraging next steps that will be coming along. So what I'm going to do now is move gears to where we've got a little bit more progress. One example is say for instance the Sydney and homogeneous burner, and where we've done some collaborations with Gaetano at KAUST on some Raman measurements. So the general premise of this burner is that we have a fuel jet central, and then so this fuel jet here, we have an annulus of air, and we have a pilot ensuring initial reaction. And so we vary the recess of this this fuel jet to explore different stability of the flame. And so some historical data, if we were to look at for methane, the general idea is that we would expect if we've got our fuel and air mixed really well, maybe our intuition might say is that we should have the optimal stability. But the idea here is that when we've got that recess distance very large, we have a blow-off velocity, which is, say, anywhere along this line, but for certain certain compositions, we actually see an increase in the blow-off velocity for a recess distance that is not at 300 millimeters, maybe 100 millimeters for this particular plot that's been presented here. Okay, so we've got some sample flames that we were starting to identify with ammonia mixed with various amounts of hydrogen. This is a photo of one of the flames in Gaetano's lab of the ammonia flame, and you might recognize this to some degree from the ammonia workshop conference page. And perhaps one of the motivations there is that we've at least got some data for this coming in, and so we want to try and market this as this is looking promising. So again, as a starting point, what we do with this flame is we try and understand what's the blow-off limit. And the idea is that with some of these flames, we've got a blow-off limit on the vertical axis, and this is the recess distance of that central jet tube. And so the blow-off distance is a function of the recess distance of that central jet tube. We've also looked at a number of different ammonia percentages, or equivalently hydrogen percentages mixed in that central jet, and we get different blow-off velocities. So we needed to select some cases for further study, and so with reference to the blow-off velocity, here's two cases: one with a recess distance which we would typically call near optimal, and one with a recess distance which is what we would generally term closer to homogeneous. So I'm not going to go through the analysis of this data, other than to say that we've got some encouraging detailed multi-species Raman measurements we've had good progress on the processing. It's coming along. We've got some data here to show that it's been processed. We're going through the analysis right now. Yes, we've got, you could say we've got mixture fraction, we've got temperature for these sorts of flames. We've even got, in some cases, a radical NH2, and that comes somewhat as a bonus. Now, for those that are, and the vision for this is that where are we going with this data is that essentially we've identified some conditions that we would say is ready for modelers to start to model. We can give the boundary condition for these cases. The final stages of the processing of this is coming along, and I would encourage the modelers in the audience far and wide to contact us to let us know. We can distribute the boundary condition information, and as soon as it's relevant to distribute to you the scalar data for model validation. And so I don't want to pin this exactly, but I would say that we'd be looking towards pushing this data out to the community somewhere around December 2023. And our aim very much is to be using this as a validation data set at the next TNF conference. So unfortunately, we would propose that it's not going to be symposia ready if you're going to be modeling it, but I would say, contact us, and this is looking like a great data set that's following on. So a small add there is that we've also got some work in with regards to a hydrogen flame, no ammonia. The idea is that at least in some cases, and this is why it's relevant to the ammonia communities, is that you might consider this a completely cracked case, but there are some challenges with ammonia flames or ammonia mixture flames that sometimes can be fished out or explored a little bit deeper by just eliminating the ammonia completely. And again, the idea, we're a little bit further along on this in that we're, yes, we do have the Raman measurements, so the temperature, mixture fraction, major species information, and this is going to be presented at the ASPAC by Dr. Andrew McFarlane later on. And so this is currently in the write-up phase, and contact us for the data if you're interested in modeling this. Okay, so right here, this is where we are with regards to exciting new cases, and I think the next step is to hand it over to Gaetano to go to where we are with these validation test cases, that next step for these next flames.
So let me go on, as Matt said, a little bit more mature data set. The data were collected a few years ago, I would say, and this is a high pressure ammonia jet flame. So with the motivation for this flame back then was really answering the question, can we do Raman scattering for temperature species in an ammonia flame? So of course the answer is yes, that's why we're here. And to start, we put ourselves in a little bit simpler situation, high pressure, and this is a little bit counterintuitive coming from hydrocarbon flames, but there is a lot of advantages from a diagnostic point of view to go at elevated pressure with ammonia, mostly because of reduction of this fluorescence interference signal. I'm not going to go into the details of the diagnostics because they were already covered by Rob Barlow in the first edition of the ammonia meeting, and you can find in the already published paper. In summary, what we had for this test case was two cracking ratio, so 14% and the 28%. This is now actually cracked ammonia. We're simply simulating the composition of cracked ammonia by mixing hydrogen, nitrogen, and ammonia. We consider two Reynolds number, one laminar flame as a reference, just as a sanity check that we're doing everything okay, and the turbulent flame at 11,000 Reynolds number, so fairly modest turbulence level. What was interesting from this test case is the Raman measurement of temperature species, quantitative NO, done simultaneously with the Raman is also available, as well as a separate measurement were done later on to obtain the velocity field to PAV for non-reactive conditions. What are the questions where we're trying to address with this simple geometry? As I say, first of all, can we do Raman measurements? Also, I wanted to investigate if, because this is now a nitrogen-hydrogen mixture, our preferential diffusion effect are significant. Should they be included, for example, in the simulation? Also, we wanted to understand the effect of cracking ratio on the flame stability and localized extinction. So let me start talking a little bit about preferential diffusion. I'm sure this can be a topic for discussion later on. Start from the basic. This is what I'm showing here is the results from chemical simulation using the autonomous mechanism. It doesn't really matter for major species which mechanism you use. this is particularly the case with 28% cracking and 42 seconds to -1 plus the strain rate. Now, I'm normalizing in this plot the ammonia and hydrogen mole fraction to their original composition. I just want to show how do transport affect the mole fraction of ammonia and hydrogen. In the case simple of pointer. Okay. So the dash line, they show the results for unity Lewis number. The results as expected, ammonia and hydrogen go almost down simultaneously, but then we see an increase in the hydrogen compared to the ammonia. This is not a transport effect. This is the composition of ammonia. As the temperature goes up, the ammonia decomposes, increasing the hydrogen content. So the message here is clear. When you're thinking about diffusion and transport in an ammonia hydrogen flame, keep in mind that as you go to higher temperature, the ammonia will dissociate and produce some of the hydrogen. Now, very different scenario if we include a multi-component transport, where we see an initial increase in the ammonia, a very fast drop in the hydrogen. So again, this is coupled with the higher reactivity of hydrogen. Hydrogen will diffuse ahead and burn faster than the ammonia. So we see a switch in the ammonia to hydrogen ratio, with the hydrogen persisting also at higher temperature. The ammonia, as you go into the flame, so you go into the breath zone, will decompose, again producing more hydrogen. So when we think about differential diffusion effect, we need to couple it with the higher reactivity of hydrogen, as well as the decomposition of ammonia entering the breath zone. So does it all matter in turbulent flames? Let's use a better definition of differential diffusion rather than looking just at ammonia and hydrogen. Let's look at the elemental mixture fraction. So we're following the N atoms and the H atoms. So if hydrogen diffuse, we see an increase in the elemental hydrogen mixture fraction independently of the fact that it's reacting or not. So this is results for the laminar flames. They agree in the average reasonably well with the numerical simulation. Unfortunately, these results are quite noisy because this is different than what, compared to what you had in hydrocarbons. But in the definition here, we have nitrogen both in the fuel and in the oxidizer. So this denominator is very small, and this amplifies the error on the elemental mixture fraction of nitrogen. So if you look at the mean, the results are reliable, or at least qualitatively indicating where differential diffusion plays a role. So let's go to the turbulent flame now and repeat the same exercise. I'm focusing on the 28% cracking because it has more hydrogen in it. Now the results, as expected, this is turbulent flame. They're not going to follow exactly the predicted profile from a counterflow laminar flame simulation, but we see the preference, the preferential diffusion acting up to 10 diameter from the jet and then becomes negligible. Okay, so this is results consistent with what we've seen in hydrocarbon flames. Preferential diffusion effects are important in the near field. They become less important in the far field. So nothing new here. But let's go again looking at this ammonia to hydrogen ratio, and let's see how it compares to counterflow simulation. Okay, the data here at the different 0D are for experimental data and comparing it to some simulation. Okay, not surprising, it's somewhere in between the unity Lewis number approximation and the multi-component description. So this is telling us that the preferential diffusion have a role, but they are not dominating. So there is of course also turbulence transport that modify this plot. But let me go to the case with more hydrogen. Of course, increasing the hydrogen, differential diffusion effect will increase accordingly. What's interesting here in this plot is that as we move away from the nozzle, so you see 1 diameter to 20 diameter, we're going to see a region where the ammonia to hydrogen ratio is going to increase. So it's plateau in this direction as you increase in the distance. So differential diffusion effect, they act they dominate in the near field, as I say, up to 10 diameter. But because hydrogen is being transported away from the center jet, have an effect also downstream, modifying the composition of the jet. This is further proved by this other simulation that we ran. We consider a unity Lewis number, okay? So turbulence mixing dominates, but we adjusted the composition to reflect the hydrogen being depleted from the central jet. And we see a fairly good match with the unity Lewis number. So going downstream, as expected, turbulent mixing will dominate. Unity Lewis number approximation will work fairly well, but we need to account for the change in the composition as we go downstream. Now let's go a step further. Professor Long group at KAUST, particularly Suleiman, his PhD student is here, is also going to have a talk at the aspect of a different flame, but they performed LES simulation using this principal component transport approach, and they compare results using unity Lewis number and the mixture average transport. So these are results in mixture fraction space. The red curve is the unity Lewis number approximation. The green curve is using the more detailed transport using a mixture average approach. None of them is perfect match, but we definitely see a significant deviation of the unity Lewis number approach, not only in the near field, but it becomes even more important in the far field, in particular for ammonia and hydrogen. This is confirming that the differential diffusion effect acting in the near field have an effect also on the far field. So they need to be included somehow in the simulations. In terms of localized extinction, these data sets also offer some challenge from for the simulation. The 28% is sufficiently away from the blowout, and we don't see any localized extinction. The 14%, much less cracking, so higher concentration of ammonia, shows a large amount of localized extinction in the range between 15 and 40 diameters. So this is could be a potentially interesting to check turbulence chemistry interaction model. In particular, if I zoom in this region where I have localized extinction, and we do some conditional averaging, we see a bimodal distribution. So conditionally averaging near the stoichiometry. So take a narrow range near the stoichiometry, where if I don't have localized extinction, all the samples should be fully burned. Instead, if I look at the 14% cracking case, I have a bimodal distribution with a peak in temperature around 2000 Kelvin and a secondary peak around 1000 Kelvin. Looking at the composition, we see that the fully burned sample don't have any ammonia and have a little bit of hydrogen, so about 2 to 3% of about 2% of hydrogen. The unbound, where localized extinction happens, the temperature is now really 300 Kelvin, it's about 1000 Kelvin. And what's interesting is that ammonia is largely unburned with a peak around 10% of mole fraction, and the hydrogen goes down to 2-3%. Okay, so this is still we're trying to interpret what does mean. This mean, and this data set was not for the different flames with higher hydrogen contact. We will give more insight in this process. I'll get back to this at the end of the talk. Now, in terms of numerical results, unfortunately, the simulation was able to capture really well the species. I would say the temperature profile was fairly accurate, but when we look at the extinction, doesn't seem to capture exactly the phenomena. In the simulation, we don't see a big difference between the 14% and 28% case in terms of localized extinction. Another interesting comparison is for NO-LIF measurements. Those were quantitative measurements. Some discrepancy in the near field, but then very good agreement in the mean, at least, as we go downstream in the flame. Again, these data are available, they're fully available. The papers have been published. The simulation papers have now been submitted, but the data are available for anybody who is interested in simulating these flames. Let me change topic a little bit. This is more recent, so I don't have as much data to show. And this is a collaboration with Bassam Dali and Angim at KAUST and my group. KAUST is a bluff body burner configuration. I put this diagram here. I'm not going to go in the laser diagnostic, but it was a major effort to go from this high pressure measurement to atmospheric pressure measurement in the lab at KAUST. This is a little bit more complex setup, also featuring a polarization separation approach to remove fluorescence interference, but was not used for this particular data set. Now, let me talk briefly about this burner. Many of you might be familiar with this. This is a bluff body burner. It's been explored by Bassam Dali for decades. So a lot is known about this burner. It's a classical configuration, but still extremely interesting. In particular, in the ammonia framework, the main question we were raising is, can we use the recirculation region as an in situ cracking mechanism? So we have a high temperature region where ammonia is trapped and eventually will dissociate, producing radicals and producing hydrogen more reactive. So we're exploring this strategy to stabilize an ammonia flame. Particularly of interest could be, for example, in a furnace where we still want a large flame, but we want to have a high Reynolds number, a high flow rate. So this and this can be achieved by in situ cracking of the ammonia. So we want to investigate this mechanism. I talk about preferential diffusion. Again, this is an excellent platform to study preferential diffusion because coupling a high strain region, the mixing layer between the central jet and the core flow, with the recirculation region will enhance the preferential diffusion effects by trapping the hydrogen, the diffused hydrogen of ammonia, in the recirculation region. So we had two series we performed in terms of Raman measurements. One with a constant Reynolds number about 5,500. So unfortunately, it's relatively low Reynolds number. And we are changing the cracking ratio from 16% all the way to fully cracked. So a nitrogen flame, you can see a very big change in the luminosity of this flame as you suppress the NH2 star and the NTO star from the luminosity. Unfortunately, this is a more complex geometry. So when you change the Reynolds number, because we're also changing the composition, it's changing the momentum flux ratio, and this determines the change in the shape of the flame. Another series we done was for constant momentum flux ratio. So this is, I'm referring to the ratio between the momentum of the jet and the momentum of the co-flow. Again, changing the cracking ratio from fully cracked to 16% cracking. And as you see, this flame geometry is maintained with a fairly large recirculation region as the process is dominated by the momentum flux. So unfortunately, the data at this stage are very preliminary. We're still going to this fairly large data set. As you saw from the pictures here, the flames are incredibly luminous and is also producing a large amount of NH2 in this recirculation region that gives a strong fluorescence interference signal. So there's some significant challenges in processing this data. So it's taking a little bit longer, but the data set is there. So let me answer some of the immediate questions. Does it work, this system, in breaking the ammonia and ideally get this configuration where we only have ammonia, we only have hydrogen, nitrogen in the center jet? We're far from that condition. As you can see, this is for 0 to 1, so one jet diameter. So it is not specified here. This is one jet diameter away from the nozzle, all the way to 15 jet diameters, going so from the recirculation region, entering in the next zone of this flame, the high strain rate region. We're comparing in this plot the 16% cracking with the solid line to the 33% cracking, the dashed line. The flame for this momentum flow ratio is stabilized at the edge of the bluff body, so in this region here. So we don't expect any non-unity Lewis number, not preferential diffusion effect. We don't expect any differential diffusion effect in the flame because it's coming from a region, the recirculation region, where the hydrogen profile is fairly flat, so there are no strong gradients. One aspect I want to point out is the role of differential diffusion in the interface between the central jet and the recirculation region. At 0D01, so these blur curves here, dark blue curve here, we see a sudden drop of the ammonia to hydrogen ratio that slowly recovers as we move away from the center jet. When you move away from the nozzle, so moving in along the axial direction, the ammonia to hydrogen ratio doesn't show this strong reduction, it increases. And interestingly, same profile, same phenomena we saw in the jet, the simple jet flame, the ammonia to hydrogen ratio then increases as you go in the neck region. Okay, so hydrogen gets depleted, is trapped in the recirculation region and burns ahead of the ammonia, creating a lower ammonia, a higher ammonia to hydrogen ratio in the eye strain, in the neck region. We're also developing, Professor Bassam is working on a new version of the burner where we have the capability of changing the co-flow velocity, so we can have we don't have to change Reynolds number and co-flow and momentum flux or composition and momentum flux at the same time, so we can have isolate the two phenomena. Now, one interesting result that was observed by Professor Dali Bassam's group was in taking OH-Cliff measurements, they detected, particularly see this image here, sometimes in instantaneous shot, a double or even triple layers of OH. So we wouldn't have just a single flame front, we would see multiple flame fronts. So the first, talking about ammonia, we immediately think, okay, this has to do with ammonia chemistry. This is why it's always good to have a sanity check and go back to a fully cracked, okay, so a hydrogen flame, and we observed very similar behavior, this multiple OH flame front, okay? So it's nothing to do with ammonia chemistry. This is purely a fluid mechanics transport phenomena that we're looking at, with the addition of the higher reactivity of the hydrogen that's present in both flames. So we applied our Raman measurements to these hydrogen-nitrogen flames, so fully cracked ammonia. We did it for 3 different Reynolds numbers ranging from 2,500 to 11,000. Okay, so just to see also if this was related to the Reynolds number. Doesn't seem to change much with different Reynolds number, but let me go to the main result here. So we have simultaneous measurement, quantitative of all the major species, temperature, and OH. Okay, so this is a instantaneous, what I'm showing you, instantaneous OH profile. We condition our Raman measurement dividing on the data based on which peak they belong to. So the strong OH peak or the weaker OH peak. And then we plot the data, this conditionally selected data, we plot in mixture fraction space. What we say is for the data in the region, so this inner peak here shows the classical non-diffusion flame behavior. So this is a non-premixed flame. So the classical non-premixed behavior of temperature versus mixture fraction, as opposed to what we see in this red curve here, where we have a rapid increase in a very narrow range of mixture fraction, suggesting the potential of some partially premixed combustion for this pocket. Okay, if we take instead if the weak OH layer appears on the left side, so toward the inner region, so toward the center jet, we see again something suggesting a partially premixed behavior, but for the rich, with a rich formation, a rich composition. Again, we team up with Professor Ron's group to do, and again, this is work from Suleiman, who's been doing really excellent simulations. Now trying to understand if we can model this phenomena. These are the simulation, of course, have much more insight. We're still working on getting all the information from the simulation. This is really truly work in progress. We were discussing about this just last 2 days ago. So let's take a slice from the simulation, matching what we will see with the 1D Raman. Okay. So we see these multiple layers, OH as well. I mean, not really in this picture, but I'll show you in a few. But if we have this additional OH layer, this was our, on top is our experimental behavior, on the bottom, the numerical behavior. So they're matching, they can extract from the simulation this OH region. I'll show you better in a movie with the LES simulation. Movie is always telling much more. Just a second, but they're not matching the microfraction profile simply because they're using a flamelet based approach. So it's not the potential for a partially premixed combustion is not in the model. Now, similarly, they can detect this OH region in the inner region, but again, not matching quite what we see in microfraction space from the experiment. But this can give us some insight on the mechanism in which these OH layers are formed. This is now I'm going to talk about the outer layer. Pay attention to this area here. This is now, you can see in this region, this OH region being shedded from the main flame and going into the co-flow. Okay, so this is what, and this is what we're saying with OH flame. Now you also can see some of this pocket from the inner side. This one we're still working exactly how they're going to be generated, but for the inner recirculation region, what the LES is telling us, these are they're not disappearing, they're simply getting in and out of our imaging plane. So I'll show you this in a second. Again, pay attention to this region where the arrow is, and you're going to see this OH pocket coming in and then slowly getting out of the plane and then sometimes coming back. So still a lot of data that needs to be analyzed, but it's very interesting phenomena in this fairly basic configuration. Now I'm just going to close with just a preview of another data set that we're working on. This is the Sandia piloted Burnham. So, oh, sorry, I have wrong picture. This is the flame. So we did, we consider in this case only 40% cracking. So high hydrogen contact, about 40%, 45%, so even higher than ammonia. This test case was specifically designed to look into the extinction region because I want to understand more what's happening as you go to high, in the high extinction. So we have 3 flames mimicking the classical Sandia DEF series, slightly different, but we go from 26,000 to 36,000 in terms of Reynolds number, so much higher Reynolds number than the other flames we look at. So this is the flame D, then this is our flame E. I want to point out in particular this region that promised to be interesting. Unfortunately, we haven't the data analyzed yet, where you see a change in the color going from the typical orange of an ammonia flame to this more bluish flame that we see in this region. And this is even more and similarly evident in the instantaneous shot here for the flame F. You can also see clearly where the extinction is going to happen. So this data set is under evaluation. The data were collected. Again, hopefully it's going to be made available to modelers. Now I want to close with some points for discussions that part of it was from discussion. So this was put together by Matt. I'm presenting it, but Matt put it together, partly from a this morning breakfast conversation with Bassam as well. So very recent. So those are I can leave it there here, but mostly we have used the same philosophy so far in treating ammonia flames, the same as we have done for methane flames in the TNF workshop. Okay, so same paradigm, same kind of series. The point for discussion is, should we revisit this approach? Okay, what progression? So the burners, there is a lot of value, both from us experimentalists, but also for modelers, to use the same burners that we've been using for many years. But is the series that we're looking at the right direction? Differential diffusion, I spent some time in this conversation to talk about it, but it's really important for turbulent flames. So this is a topic. Extinction, because I believe we should focus on. But then, is there some specific ammonia-related phenomena? For me, the key one to address is this pyrolysis, so this cracking of the ammonia in the high temperature region. This is something it's not really it's specific, let's say, to ammonia, especially in a configuration with partially cracked ammonia. For the measurements, we can have a wish list that's very long. Many of them might not be ever satisfied. I think there's common agreement that we need the simultaneous measurements of temperature, major species, but with some of the key radicals. We put NO, NOH because it's Matt and I that did this list, and we know we can measure NO, NOH, but personally, I believe we need to measure NTO, we need to measure NO2. I just don't know exactly how to do that. So NO2 is easier, but NTO is going to be very challenging. Okay, and of course, there's a lot of other flames out there. I did something that was not my intention originally. I really hope that in 2 years, when we have again this meeting, I'm not going to present the work from KAUST and Darmstadt only, the more players come in with this detailed level of measurements that we need for model validation. So I hope the more players will join us. Okay, yes, that's it.
Thank you very much. So, yeah.
Come back. The question is going to be also for you.
Yeah, but the time is already over. So that,
no, but there is no.
yeah,
I mean,
we accept some comments.
So there is this conference. My intention is that really discussion should be the key point. So there is a poster session following this. There's going to be probably, I don't know if we have a coffee break, but there's definitely a poster session, and then we have the dinner. But the program is loose enough that we can allow for going over time, and if there is a good discussion, we should continue the discussion. So let's go for the discussion.
Nice presentation to both of you. So thank you. The question is about the bluff body burner, Bassam's bluff body burner. That double reaction zone, dual reaction zone, is it because you got an extinction event upstream, so that you got a penetration of, you got a concentration gradient that forms in the event just downstream? Or is it the fluid that's convected from the recirculation zone downstream, so in the upstream, so then you should see it right across the flame? Or is it because ammonia chemistry is separating due to differential diffusion and then forming this dual reaction zone?
I give a guess. Okay, so this is still a very fresh material. We're still discussing it, I believe. I think there's going to be different answer for the outer flame, the one that's in the lean region, and the inner flame. What the LES, we have a LES data set. What I'm convinced is differential diffusion doesn't really play a big role in this. The increased hydrogen reactivity, we do have hydrogen in these flames and also in the ammonia flames. Hydrogen is more reactive than methane. And so the Reynolds number is fairly low, 5,500 for this flame. So but we also saw it for 11,000. So it doesn't seem to change significantly with the Reynolds number. We see this double layer going from almost a laminar flame at 2,500 all the way to 11,000. So it's mostly fluid mechanics. And this is in agreement with the fact that the simulation from Aung's group using a flamelet-based model. So even if there is, so it's really transport-based. So what I show in the simulation is a shedding of this OH from the flame front going toward the outer region. That's the mechanism we have identified for this lean OH peak. We still have to understand. Maybe Suleiman has a quick answer right now because we asked him to look into it. If there is, so this is, no, in the recirculation zone, we don't see this. This is in the neck region. Okay, so this is something happening in the neck region that we see this phenomenon. Okay, so we're looking at, the one question I have is if this is producing, if there is any heat release associated to this OH peak, or is simply being transported around. Some of the data suggest there is also some heat release, but those are instantaneous shots we've been looking at. There's a lot of work to do, and the simulation can help. What we see instead in the inner is this intermittence happens in a region where there is also high vorticity. So this doesn't necessarily indicate that the flame front is being extinguished, but it may simply move in and out of the plane. Unfortunately, this is a limitation of a planar OH, or even worse, 1D Raman OH measurement. We're only looking at a single plane. So it goes outside the plane, we lose it, and goes back to the composition of the recirculation. Differential diffusion, I don't think plays a role here. But Sam, I think, wants to add something.
I think Gaetano covered it all. We just as intrigued why such a thing would happen, and we didn't see it before in all the bluff body measurements that we did, especially in the imaging. And the only interpretation is along the lines that Gaetano has articulated, is perhaps hydrogen is resilient enough to stand in an island and basically burn on its own without being extinguished, while in a hydrocarbon flame would not have the speed for it to actually survive, even as being stretched sort of vertically. What causes the separation could be the conditions by which the Reynolds number is not too high and it's sufficient shedding, both shedding from there that actually allow it to separate and still survive the flame. I presume we done a lot of hydrogen flames in the past, but they weren't diluted this much. And then I'm assuming then the flame is more resilient to the shedding, and hence it did not see it before. We tried to go back and look at imaging of similar flames in the past, but nothing came up anywhere similar. That it was there, but we didn't see it. So of course, within there's extinction and so on, it should. This is not too difficult to find. But I think the key was that hydrogen-nitrogen flame gave us this, as well as ammonia-hydrogen flames. And that's where we're saying, okay, well, it's not really an ammonia thing, it's a hydrogen thing, or hydrogen-nitrogen mixture.
Did you try a similar hydrogen, say, methane flame with the same Reynolds number?
No, we didn't. Remember, we done this in Sydney of two hydrogen, one methane, same geometry. In fact, no, it's 2 to 1, yeah. And we done imaging. Looked at my thesis, I couldn't find anything similar, so which is interesting. And we had 10,000, it wasn't 5,500.
Right.
So I'm leaning towards, okay, this is something to do with the hydrogen.
And commenting on the extinction, this is happening with hydrogen flames, and we're far, far away from the extinction. Yeah, so it's not an extinction related. That was my first guess. When I first saw this picture, I thought it was some localized extinction and reignition. Looks like it was wrong. So that's
the interesting bit where the lean premixed and rich premixed basically jump right to left in a way, where the flame burning inside and outside. It sort of changes places as we go, which is also an interesting phenomenon.
But in many shots, we actually have both the inner and the outer. So it can be anything. This is why I believe there's two separate phenomena. They just happen sometimes at the same time, sometimes they're shifted. There's intermittent.
Interesting in some of Ran's work that Suleiman did, we almost see two flames hugging each other, like an inner flame and an outer flame. Of course, it's not real because in reality, we see a continuous flame. When we done the LES, we could be able to actually see it instantaneously.
But if it's purely a transport phenomenon due to the differential diffusion, then you've got, if you do the hydrogen methane flame, right, so similar molecular weights, same Reynolds number, then that should be reproduced, except for the fact that you've got methane. That even if the reaction zones separate totally, you've got a hydrogen one, you've got an inner one that is the methane. So you should see both then, right? If it's purely differential diffusion. If it is not, if it's due to the ammonia chemistry, then you would see it only in the H2
we know it's not
ammonia
ammonia.
flames.
We know it's not ammonia chemistry because we see this with nitrogen-hydrogen flames. So that's the first thing we wanted to eliminate.
Oh, you see this with the right?
The results I show is for hydrogen. So
Right.
we wanted to eliminate both the potential for an extinction ignition. So we move away from ammonia. So it's very much more stubborn flame.
Yeah.
And then with hydrogen, so the ammonia chemistry is out of the picture. It's purely hydrogen.
Right. So you should be seeing it then with a hydrogen methane flame of a similar proportion and similar Reynolds number.
Yes. Possible.
The stoichiometry is likely to shift. Remember now with nitrogen.
Yeah, it will shift a little bit. Yes,
So it'll be closer to the shear layer. So with nitrogen, we weigh in, and that may be also influencing what's happening here.
Yes, very good presentation. I'm Namil Kim from KAUST. I have a very simple question. You show the Reynolds number, but did you compare the local velocity near the tube exit with the burning velocity or turbulent burning velocity? So I mean, when you do experiment with methane, it will be very easy to blow off. But in your case, in your experiment or simulation, did you check the velocity or the blow-up condition?
You're talking about the bluff body burner?
Yeah.
Okay, so for the Reynolds number we're referring to is simply the Reynolds number at the jet exit. Okay, so this is based on the density and on the composition of the mixture at the exit, so the fuel, and has really nothing to do with what's happening at the flame front, because the flame actually depends on the momentum ratio. The flame will shift from the edge of the bluff body, where the velocities are definitely much lower, because that's a recirculation region, and all the way.
So my question is
inner,
from the viewpoint of edge flame. So its propagation velocity can be compared with your local velocity and the flame structures.
Yeah, but that has to be done at the location of where the flame is stabilized. In this case, for many of the flames,
so if we use a small tube with the same Reynolds number, we can easily make a lifted flame.
Yeah, I mean, it depends on your bluff body, and it depends on the momentum flux ratio. So it depends on the co-flow velocity. It will shift the flame front. So in this series we have here, this is the flame front. It's stabilized at the edge of the bluff body.
So did you check the local?
We haven't measured the velocity there, but I expect that to be a very low velocity. That's the nice thing of a bluff body stabilization. So now if we move and I have, if we change the velocity of the inner jet compared to the outer jet, we get, and this is what we did for the hydrogen case, the flame front shift going from the edge of the burner, you see the OH layer is here, at the edge of the bluff body, it shifts all the way to the center jet. So if we are in this configuration, the configuration of flame C, okay, then the Reynolds number is a little bit more meaningful, because that's where the flame front is actually stabilized. Here I expect a very low velocity, and unfortunately I don't have the velocity fit. So it would be nice to do it. We don't have it, but
Hello. Yeah, I want to have a comment about say a comment about the differential diffusion. So when you're doing hydrocarbon flames, you basically have hydrogen and carbon who are basically racing to the reaction zone, and then hydrogen reaches there first, so it captures the oxygen earlier, and then so the ratio between what you end up at different position is different, and hence the structure of the flame starts to be different, mostly because they burn different rates and so on. When you have ammonia and hydrogen, the product is still water. So where it forms doesn't really matter much. So I was looking at Matt's results, and I could see that almost there's no difference in the temperature, where you could see a little bit of variations on the rich side, but in the lean side, it's actually over the reaction zone. Now, I wanted to talk about this as well. I mean, you seem to show there's a shift in the stoichiometric. Now, if you're calculating it correctly, it should not shift. Yeah, if this is the Bilger's formula, it should sit in the same place. It's just the distribution will be different. So I was wondering about how do you end up with water sort of happening more on the lean side, I guess. So well, what I'm trying to say is, maybe you alluded to it in some sense, is that in turbulent flames, it's unlikely to be an effect, basically. What you saw at low strain rate in lemon flames is interesting, but in practical flames, it's unlikely to be an issue, is what I'm trying to say. So if the implications is, what I'm saying is that in turbulent modeling, it may not be a major issue if you have ammonia hydrogen flames. Well, my counter argument is that, of course, I welcome more people simulating, and they're welcome to use the unity Lewis number approximation. But my expectation is that if you don't include this effect, at least in terms of compositions, you're not going to be able to match it. Temperature effect might be small, but with hydrogen, no unity Lewis number might need to be considered, okay? Because it would just a small increase in temperature might affect your ability to match the NOx properly. And this is really why these data sets are for people to test. And of course, we all hope we don't need to use a complex transport model because we want this simulation to be cheap. And I think in any case, it would be good to know what the error of you're making is, because of course, for industrial application, we want the simplest model possible. So knowing that, let's say, you're just going to be making an error of n% on your estimate would still be a useful result to understand how far can you go with a simpler model. So I think there is value in comparing results with and without the unity Lewis number approximation or mixture average. I don't think we need to go to the full multi-component transport. That would be a overkill. But I think there is value in this, and that's for the community, I guess. Sure. You want to comment on that?
More things to talk about.
All right. Maybe I could add another comment about extinction and reignition. I wonder if the mechanism is the same as sort of hydrocarbon flames. Perhaps imaging would help. Something we're intending to do to see what is happening there and why, and how it ignites. And well, you know, of course, it's much easier to extinguish an ammonia flame. And how does adding hydrogen helps or hinders? Well, supposedly helps, reduces the extinction, but it may impact on the reignition. So one way is to use this bluff body that we have, because in the extreme case, we did see extinction in the NIC zone and reignition after. So we collected some of the ammonia that escaped and so on. Understanding that actually it's another thing that would be of interest. Commenting on the comment, the data sets with extinction for the bluff body are in processing, so we'll evaluate more in detail. The only limitation of this particular data set that we already collected is not a limitation of the burner, but just of the data we have today,
is the relatively low Reynolds number. So if we're talking about turbulence chemistry interaction, the additional set we took with the Sandia parallel burner, and to pretty much the same extent the homogeneous burner, allow us to go to higher Reynolds number and provide a little bit more insight. But those data are available.
Can I have like a small request? Could we move away from flame E and D and so on, and be a little bit more imaginative in describing it? I mean,
true, but it's.
I just blame Barrow for that. That's all.
Yeah.
Thank you, Giancarlo Sorrentino from CNR in Naples. I have a question for Matt. The hot co-flow images that you showed, I mean, the composition of the co-flow is Barnard gases, or there are also some radicals?
Well, I'm not sure particularly which slide you're referring to, but maybe to give you a rough indication that when we were running the experiment, okay, one of the variables that we were varying was the hot co-flow temperature. And another variable that we were varying was the percentage of hydrogen in the jet. So we have ammonia with some percentage of hydrogen in the jet, and that was something that we're interested in varying. And we observed different sensitivities in different regimes. And likewise, we could keep the jet composition fixed and change the co-flow temperature. So one of the slides was co-flow temperature constant with different percentages of hydrogen. And there was summary plots of the liftoff height, you know, with the horizontal axis either hot co-flow temperature, or with the percentage of jet hydrogen constant at the plots, or the other way around, hot co-flow temperature. Does that answer the question? So we were in effect varying two parameters, right? The idea was to try and understand the parameter space. The parameter space is large when you've got two parameters that you're varying. If you're going to be doing detailed measurements, you can't measure hundreds of flames. You've really got to narrow it down to two or three small, succinct sets.
Yeah, I was just wondering if there are, I mean, if the co-flow is equilibrium products, or there are also some radicals that can influence, of course, the stabilization process.
Right, okay. So perhaps we could, the short answer to that is that the hot co-flow is about 70 millimeters upstream of the jet exit. And we know that it's awfully close for everything that matters with regards to minor species to equilibrium. Obviously, things like nitric oxide would be slowly varying, but these are at very trace quantities because of the relatively low temperatures.
Okay, thank you.
Okay. So that there's no questions, so I will close this session. So thanks to Matt and Gaetano.
Thank you. So now we have only the poster session left for the. I guess we have a few posters outside, and maybe do you have any direction for the social dinner? So there is a dinner tonight at 5:30, right? That's what is on the schedule. So immediately after, yeah, okay, 5:30 at the Shangri-La Hotel. That's just across the street, pretty much. So I hope to see you all there.